This video is going to be about capacitors. We have talked about resistors, and they are a very useful thing in a circuit. A capacitor is something that's going to act more or less as a storage tank. So a capacitor is all about storing charge, and anytime we are storing charge, if we have electrical charges that are stored into a space and they're separated by some distance, we know we can get a potential energy out of that. So a lot of times you'll see a capacitor listed as something that stores energy. Both are true. The idea is this: if I've got two plates like this, and I can connect a battery to them, that battery wants to push current in this direction. These two plates have, their own properties. They are going to act as my capacitor. I want to push current in this direction. These are conducting plates, so I can keep moving charges down and down the line. And if these are conducting plates and they are reasonably big, I can dump some extra charges on here. So this top plate will become positively charged over time. With a wire, I can't really do that, because a wire, you can think of a wire as almost having our charges in a single file line. It's not exactly accurate, but it's not too far from the truth. So with this, I don't have to have these charges all in one line. Because it's a big plate, I can spread those charges out a little bit more. Now, any of these positives that are over here, they come from negatives that are on the other plate. Because if this thing was at first electrically neutral, then in order to move a positive to this plate, I have to have taken it from this plate. I used to have negatives and positives together. I stole those positives, moved them down the line, and now I've got a negatively charged plate and a positively charged plate. A quick aside, yes, I know that it's actually the negatives that are moving a lot of the time. There are different models for current flow, but I know that I'm not moving, protons necessarily or anything like that. But we model current as being the direction of flow of positive charge, so we're going to pretend that it's positives that we're moving, because that's the direction of the conventional current. Just go with it a little bit. So I have these charges, I have these positives, and these positives, they want to go back. They don't really like having a whole lot of positives together in one spot. That's electrical charges are a little bit asocial like that. So this positive charge doesn't like being on a plate with all these. It wants to go back. However, there's this battery, and this battery is acting, again, like a hill, kind of, right? That positive can't climb that hill to go back, so it's kind of stuck. Also, that positive sees all these negatives on the plate below it, and it's still going to be attracted to that. So we have a desire to go back, we have this current, or we have this battery that's trying to keep us on that plate, and we have an attraction between these. And together, there is some kind of a balance point where the charge on this plate will be steady, and the charge on this plate will be steady. And that's kind of our saturation point of that conductor. At that point, the charge on either plate will be equal to C times delta V. Delta V is what this battery is supplying. That is its job. And C, that's a number that we need. This is called a capacitance. With a resistor, we had a resistor, and that was the thing. And then we had the resistance, and that was the property. With a capacitor, our capacitor is the thing, and our capacitance is how good this is at being a capacitor. So a higher capacitance is able to store more charge. A little bit more to add to this. We talked about how a resistor could be defined based on some of its properties, that a longer resistor is going to give you a higher resistance, a bigger area is going to give you a lower resistance. We should be able to do something similar with a capacitor, and we can. If we've got these two plates, it should be a reasonably logical thing that the bigger these plates are, the more charge we can dump onto them. If capacitance is going to be a measure of how much charge we can dump onto plates per unit volume, or per unit voltage rather, then it should make some amount of sense that if we have bigger plates hold more charge. So we're going to have a capacitance that is higher if we have a bigger plate area. And here's the funny part. It would make some amount of intuitive sense to say if these plates are farther apart, we'll be able to isolate our charges more. And that would be true, but this positive charge is sitting and it sees this negative charge, and because it sees a negative charge, it's going to be attracted to that negative charge, which means this positive wants to be drawn downward. Otherwise, there are a lot of other positive charges on this plate, and that positive charge will want to go back up. So there is a balancing act, and if these charges were completely free to go, we would want them to be able to stay on this plate. So if we bring these plates closer to each other, if we have a separation distance d and we bring these plates closer to each other, then we're going to find that we can actually put more charges on this plate. We can stabilize it. So our capacitance is going to decrease with the distance between them. And just like before, where we had this coefficient that just depended on the material, we're going to have a coefficient here that depends on the material. The material that we are interested in is actually the material that's between the plates, not the material that the plates are made of. So if I have empty space between here, I'm going to get a permittivity of free space. We have seen this number before. When we were doing electrostatics, when we had like a force equals K Q over R squared very early on, we defined that Coulomb constant in terms of the permittivity of free space. We didn't really do a whole lot with this, but it was always there. So that permittivity of free space, that's 8.85 times 10 to the negative 12th, and that's going to have units of meters squared per Newton Coulomb squared, which is kind of a strange one, but we can also say that is farads per meter. Capacitance has units of farads, which get a capital letter F. A farad is a huge capacitance. We generally deal with numbers in the nanofarad range or even picofarad range. Sometimes we'll get into microfarads, but we're talking really big capacitance values at that point. What if we don't want to keep empty space between these? Can we do better? If we've got our plates like this and we want to put something between them, we could have a plate and a plate, and we can put something between these. Some kind of a material between these. That material that we put between these is called a dielectric. A dielectric is something that can polarize and that can kind of stabilize this thing a little bit more. The interesting property, the relevant property, is what we call our dielectric constant. Which unfortunately gets the letter kappa, which looks a whole lot like a K. A dielectric constant is just going to be a multiplier. We are actually going to just stick it right here in this equation. For empty space and for air, our dielectric constant is 1. For air, it's 1 with a few zeros, and then we start to get non-zero numbers. But to 3 significant figures, we're going to get something like that. For paper, we get something like 3, maybe 4. If we were doing this in acetone, we would get 20.7 or so. The point is, we can change the effectiveness of our capacitor by adding a dielectric, and we get a capacitance equation that looks like this. That's really the extent of how much we're going to need about capacitors for their properties. I have one more piece. We said that a capacitor is something that stores charge, but then we said it also stores energy, that's equally probable or equally valid to say. So we should have some kind of an energy related to charge. The potential energy stored in a capacitor is charge squared over 2 times the capacitance. Now we can do some of this. We can say our charge is C times the potential difference, and we can put that in here. So then this is going to be a C squared potential difference squared over 2C, or if you like, a half C V squared. Or we can write this as a half Q delta V. They're all equally valid. They're all ways of relating the charge and the capacitance to the energy stored. That's the whole deal. That's capacitors for now.